Okay, so in this example problem, we're going to be examining a hydrodynamic bearing. And within this hydrodynamic bearing, we have a shaft inserted into an outer journal. Between that outer journal and shaft, we have a thin film of fluid of thickness D, which is radially applied around the shaft. And the job of this thin film is to bear the load of the spinning shaft and preserve the journal in the process. So driving this shaft is a torque applied by a falling mass M. And in reality, this torque would be applied by a stepper motor, a servo motor, or some other kind of DC motor. However, for simplicity, we can treat the torque that would be applied by one of these motors as the torque applied by some equivalent falling mass M. Now, the objective of this problem is to determine a governing differential equation for the angular velocity of the shaft, and then solve that governing differential equation to yield a function for the angular velocity of the shaft. So to begin, let's look at some of our fundamental assumptions. Our first fundamental assumption is that we're dealing with a Newtonian fluid. Our second fundamental assumption is that the fluid is both incompressible and laminar. Our third fundamental assumption is that we have a small gap width d such that we can assume a linear velocity profile in the fluid. And our fourth fundamental assumption is that our mass m starts at rest. I'm going to add one more fundamental assumption here, and that last fundamental assumption is going to be neglect gravitational torque. And specifically what I mean by that is we're going to neglect the gravitational torque of the shaft. So the shaft has some weight. That weight is going to apply some kind of torque on the shaft. We're going to neglect that self-weight torque of the shaft. So first, let's draw a free body diagram for our shaft within the journal. So here we have our free body diagram of our shaft, and we've assumed that clockwise is positive. So in these problems, we don't necessarily know the directions of alpha or omega, so we really just have to make a guess, assume a direction for those variables, and then carry that assumption consistently throughout the problem. If we do that, the math will typically work the signs out for those values at the end. So just pick a direction that you assume is plausible, and then carry that direction consistently all throughout the problem, assuming that it's correct. And then again, the math will typically work out the actual signs, the actual directions at the end of the problem. So we're assuming a positive alpha and a positive omega, or we're assuming a positive angular acceleration and a positive angular velocity. We've also assumed that our fluid torque is negative, and the torque due to the falling mass m is positive. So at this point, we're going to write out Newton's second law for rotation. Okay, so we're assuming clockwise positive. And we're going to sum the torques about the axis AA. And the sum of those torques is equal to the moment of inertia of the shaft about AA times the angular acceleration of the shaft about AA. So what are the torques about shaft AA? So we have TW, which is positive, minus TF, which is negative. And that's equal to IAA alpha A. Okay, so let's break these down one at a time. The torque due to the fluid. Now the torque due to the fluid is the torque due to the viscous shear. So let's start with our TF. So our torque due to our viscous shear. We know that we have a Newtonian fluid and that the fluid is both incompressible and laminar. So what does that mean? That means we can use Newton's law of viscosity. We have a time-dependent problem, so we need to use the time-dependent form of Newton's law of viscosity, which, as you may remember, is tau of yx equals mu times the partial derivative of u with respect to y, where u is the velocity profile of the fluid. Okay, so to start to work this out, let's draw a frontal view of the shaft within the journal. So here's our shaft. This is our fluid of thickness D, right? And that's exaggerated for the diagram. And then we have our journal on the outside here, which is just static, right? Our journal is not moving, it's not rotating. Our shaft is rotating within our journal. So just to kind of clarify, this is the fluid. This is the shaft right here, and the shaft is what's rotating. Okay, so let's kind of break out a small section of this view and draw it right here. So we have our journal in this small section right here. We have our shaft, which we'll represent with just a small little plate. And we know that our shaft is rotating, so it's moving with some velocity u. We'll call it big U. And we know that due to the no-slip condition, our fluid has 0 velocity at the journal, and our velocity, a velocity big U at the shaft. So that's velocity big U. And then it decreases linearly to 0 at the journal. And we know that this velocity profile is linear because we're using the small gap width assumption, assumption 3. Okay, so the next question is, what is big U? What is this velocity big U? Well, we know that the shaft itself, right here, is spinning with some angular velocity omega, right? So let's break out our shaft right here. Our shaft is spinning with some angular velocity omega, and it has a radius r. So a point at the very outer rim of this shaft is moving with velocity v equals omega r. So a point right here in the outer rim of the shaft is exactly this point right here, right? So we're looking at a point on the outer rim of the shaft right here in this diagram. So that must mean that big U is simply equal to omega r. Now, we know that omega is a function of time, and so big U must also be a function of time. Big U of t is equal to omega of t r. So I hope you see what I did there. I'm really just converting the angular velocity of the shaft omega to a linear speed using the radius of the shaft. So the linear speed at some point in the outer rim of that shaft is omega r. When we're looking at this diagram right here and we break it out, this point right here in the shaft is a point on the outer rim of the shaft. So the speed here is equal to omega r. And because of the no-slip condition, that must mean the fluid is also moving at a speed omega r at this point. And because we're assuming a small gap width, a linear velocity profile, that velocity then linearly decays to 0 at the journal because of the no-slip condition. Okay, so now that we have our velocity big U, we can determine the velocity profile of our fluid little u, which is this right here. So remembering that this is our gap width d, we could say that the velocity profile little u is equal to 0 minus u over d minus 0, noting that we're going to assume that our local coordinate axis here is positive y up, starting at 0 here at our shaft. So we have 0 minus u over d minus 0, and we can multiply that by y minus d. That's equal to negative u over d times y minus d. So we could check that this is correct by plugging in y equals 0, where at y equals 0, this is negative d. Negative d over d is negative 1. Negative 1 times negative u is positive u. So y equals 0, we should have u, positive u, and we do, right? And we know that this is positive u because omega is assumed positive, r is assumed positive, and so big U here should also be positive. So that is correct. At y equals d, we have d minus d is 0. 0 times this quantity is 0. We have 0. So this is the correct velocity profile for this small gap width. And now that we have our velocity profile little u, it's worth noting that little u is a function of both time and y. And that's because it is equal to negative u, which is a function of time, over d times y minus d. So here's our y dependence, here's our time dependence. Okay? So now with that, we can use Newton's law of viscosity, the time-dependent form of Newton's law of viscosity, to determine the shear stress distribution within the fluid. So we can write tau of yx is equal to mu, partial derivative of u with respect to y. And that's equal to mu. Partial derivative of this with respect to y is simply negative u over d. So we get that tau of yx is equal to negative mu u over d. So now that we're going to start writing out the torque due to our viscous shear, we should note how we've written the equation up here. So up here on the left-hand side, we have manually applied this sign. right? So we want this to be a magnitude, and we want this to be a magnitude. We do not want the torque due to our viscous shear to have a sign built in because we've already manually applied the proper sign. So we want TF, the torque due to our viscous shear, to be a magnitude. To do that, we would say that the torque due to our viscous shear, or the magnitude of the torque due to our viscous shear, is the magnitude of tau yx times the area of contact of the fluid with the shaft, which we're going to call A, times the moment arm of the viscous shear with the shaft, with the axis AA that we've outlined over here, and that moment arm being the radius r. So if we write that out, we have the magnitude of negative mu u over d AR, and we've already established that u is equal to omega r. Omega, we have assumed, is positive. R is positive, and so u, big U, is positive. Mu, the viscosity, is positive, and small d, a distance, is also positive. So the magnitude of this term is simply this term without the negative sign, right? It's -1 times this term. So it would be equal to mu u over d a r. Now, we can use this as an opportunity to break out u into our dependent variables that we're trying to determine. So we can write this as mu omega r over d a r. So we can write that out a little bit more simply. We could say mu omega, let's write that out a little bit more clearly. Mu omega r over d. Now A, the area of contact between the shaft and the fluid. That is simply 2 pi r, and we have that length here, L. 2 pi r L times r. So we have the magnitude of our viscous torque is equal to 2 pi mu r cubed L over d times omega, which we can see is a function of time because omega is a function of time. Okay, so now that we have an expression for TF, let's look at how we can determine TW. And remember, TW is the magnitude of the torque due to the weight of the falling mass m. So let's draw a free body diagram for our falling mass m. Because remember, if you go to the beginning of the problem, the weight of the falling mass m is not exactly what's creating the torque. What's creating the torque in the shaft is the tension in this cable. The tension in this cable may be equal to the weight of the falling mass m, or it may be less than or greater than the weight of the falling mass m. We don't really know until we draw a free body diagram. So that's been a bit of a misnomer this whole time. However, to determine how far off the tension in the cord is from the weight of the falling mass m, we have to draw the free body diagram, so let's do that now. So we have FBD, falling mass, and we'll have our mass m, and we have the tension force acting on the block upwards and the weight of the block downwards. Now, whenever we write Newton's second law in the linear form out, we first want to define a direction as positive before we do that. So let's assume positive downwards. So let's write our Newton's second law out. So we have the sum of the forces in y is equal to positive MAY. And when you're using Newton's second law, as a reminder, it's typically a good idea to assume that your object is accelerating in the direction that you arbitrarily defined as positive. So I arbitrarily defined y as positive down, so I'm then arbitrarily defining that my object, m, is accelerating in the positive y direction such that I can write the sum of the forces is equal to positive MAY. And then I just let the signs work themselves out in the end. If I arbitrarily define that my y was positive up, I would also write that the sum of the forces in y is equal to positive MAY. But now, I'm just arbitrarily assuming that the mass m is actually accelerating upward instead of downwards, okay? So, sum of the forces in y is equal to MAY. And by the way, that's not the only way you can do it. It's possible to assume a negative acceleration. It just tends to complicate the problem, and I typically don't do it myself. Okay, so the sum of the forces in y is equal to positive MAY. So what we're going to have then is mg minus t is equal to MAY. Now the sticking point here is determining what is AY. So if we now assume that we have a constant length, non-slipping rope. Okay, so let's draw a breakout diagram of our shaft. And let's look at 3 points. So we have the wrappings around our shaft. We have our mass M here. So let's look at the mass M itself. Let's look at a point on the rope on the shaft and a point on the shaft directly beneath that point on the rope, right? So this is on the shaft. This is on the rope. And this is the mass M. So because of the non-slipping condition, we know that this blue point on the rope is accelerating at the same rate as this green point on the shaft right beneath it. Because of the constant length condition, we also know that this blue point on the rope is accelerating at the same rate as this orange point, which just so happens to be the mass. So therefore, we know that this mass is accelerating at the same rate as this green point at any given instant because of the constant length and non-slipping rope condition. So then we know that the acceleration of the block at some given instant is equal to the acceleration of some point on the shaft at that same instant. So we know then that AY should be equal to d omega r dt. So we know AY is positive, which is consistent with how we've assumed AY to be in the equation up here for Newton's second law. So now let's write that out more formally. So we have mg minus t is equal to m d omega r dt. So now we have some of our final expressions, and we're almost done. We have the torque due to our viscous shear, Tf, and we have the tension in our rope, T. So Tf is actually the torque, as we've already established. T is not the torque. T is the tension in the rope. To turn the tension in the rope into a torque, we have to say Tw, which is the term for the torque of the weight of the falling mass. In reality, it's a misnomer. Again, it's really the torque due to the tension in the rope due to the weight of the falling mass. Tw is equal to the magnitude of T times the moment arm of the tension in the rope, R. So that is equal to the magnitude, or the absolute value, of mg minus mr d omega dt r. So if you look at the free body diagram for the falling mass that we drew in the previous page, we're assuming that the object is accelerating positive down. So therefore, AY is positive. So if AY is positive, as shown here, and we know M is positive, that must mean that MG is greater than T. So we assume that MG is positive, T is positive, because we've kind of written this as a magnitude minus a magnitude. So a big number minus a smaller number is equal to some number in between. Since this is effectively MAY and this is MG, you could see then that this is already positive. So we could just drop the absolute values. So mg minus mr d omega dt r. Okay, so we have our final torques here, which are properly signed. And now we can plug them in to our Newton's second law rotational variant. Let's yield that result now. So we have our Newton's second law rotational variant right here. The last bit of business we have before we come up with the governing dE is breaking down this moment of inertia term. So what we really need is the moment of inertia of the shaft about the axis AA. If we look at the original diagram, here's our shaft. It's a solid shaft spinning about the axis AA. And that is simply equal to 1/2 mr squared, where m is the mass of the shaft and r is the radius of the shaft. So the way we'll write this then is 1/2 m bar for the mass of the shaft, r squared, and the angular acceleration of the shaft about the axis AA is just the time rate of change of the angular velocity of the shaft about the axis AA. Again, we'll drop the AA notation and we'll write d omega dt. We'll write this ODE in first order linear differential equation form, and then we'll proceed from there. Okay, so we have our final governing differential equation here, written in first order ordinary differential equation form. And this is the governing ODE for the angular velocity of our shaft, right? So omega, again, is the angular velocity of our shaft. R is the radius of our shaft. L is a characteristic length. It is the length of the shaft within the journal. Mu is the viscosity of our fluid. D is our gap width. G is our magnitude of gravitational acceleration. M bar is the mass of our shaft. And m is the mass of our falling weight. So you can kind of see here that this is our moment of inertia term, and it essentially represents the resistance of the system to changes in its rotational state, right? This is essentially the rotational equivalent of the mass of the system. The larger this is, the more resistance the system will have to changes in its angular velocity and its angular acceleration. This term right here represents the torque due to viscous shear. You could see that 2 pi r cubed L mu over d is positive, and omega we've assumed is positive. So if we bring this positive term over to here, it is mgr minus this term. So this term is exerting a negative torque, as we've defined in the problem, or is exerting a counterclockwise torque. It is resisting the positive torque that is exerted by the tension in the rope due to the falling mass. And it is directly proportional to the angular speed of the shaft, omega. And then the last term, mgr, is just the torque applied because of the weight of the falling mass. So you have a torque applied to the weight of the falling mass, a torque term applied because of viscous shear. You have your moment of inertia term, which is just kind of a damping term, and that is all tied in with the rate at which your angular velocity of the shaft changes, which is our alpha, right? So we could solve this equation through many means. You could use, ODE 23 in MATLAB. You can use Python. You can use Octave. You can use separation of variables. I'm just going to skip to the solution of this differential equation, which I have achieved through separation of variables, and then we'll discuss the final result at the end. Okay, and this is the final solution to our governing differential equation. Omega is equal to A over B times the quantity 1 minus e to the negative bt over c, with A defined as mgr, B defined as 2 pi r cubed L mu over d, and C is defined as 1/2 m bar r squared plus mr squared, where again, m is this m without the bar is the mass of the falling weight, m bar is the mass of the shaft. So our solution form is pretty typical for a lot of these viscosity driven problems. You'll see that at initial time, time 0, that the angular velocity of the shaft is indeed 0, because e to the negative 0 or e to the 0 is 1, 1 minus 1 is 0, this difference is 0, so omega is 0, the shaft starts from rest, as we've assumed. At infinite time, you have e to the negative infinity, or 1 over e to the infinity, or 0, and this difference is maximized at 1, and you have a steady state velocity of a over b, which is just mgr over 2 pi r cubed L mu over d. So that is the steady state speed of the system, the steady state velocity of the system. You'll also notice that our time constant for the system is b over c. Okay, so that probably wraps it up for this video. I really appreciate you watching. Thank you very much, and I will see you next time.